So I have in front of me the code for a linear regression use case. Now this is the same use case which we have explored earlier. I'm looking at the bike sharing data set and I'm specifically looking at the day level data. I've kept the code ready so that we won't actually start building a regression model from scratch, and rather we can focus on calculating the metrics to understand how does a model perform. I'll just give you a quick overview. Importing the dataset is something which you've already seen, so I'm just ignoring that for the time being. I've created a function. This is something which you can look at the moment. What I'm doing over here is I've created a function called label encoder where you can pass a data frame and a particular column, and it will return to you a data frame with the one hot encoded version of that particular category. So for example, let's say you pass the bike sharing data set, which is at a day level, and you pass the column, let's say season. Now season can have values like winter, summer, and so on. And it returns a data frame where you'll have the one hot encoded version, which means that season will now be converted to a version like season underscore weather, season underscore winter, and you'll have a 10 flag. The next column would be season underscore summer and a 10 flag. So depending on the number of distinct classes you have for that categorical variable, it will actually expand a data frame and create a binary flag for each of those classes in that particular category as a data frame. So what it is doing is technically it's using the label encoder available under sklearn's preprocessing. It's extracting the different labels from that column, and it is using, after preparing the one hot encoder object, it's creating an array, and it's leveraging this array to create a data frame with the respective names as a concatenated version of the column name and underscore the class name. So let's say you have the column as season, and season has values as winter, summer, and autumn. You'll have an output of a data frame with 3 columns and the same number of rows as the input data frame. So the 3 different column names will be season underscore winter, season underscore summer, season underscore autumn. And this depends on the number of different classes you have for your categorical variables. Similarly, I have separated the categorical variables and numeric variables, and I'm passing through a loop to create a concatenated version of the entire categorical set. So let's say I have season, year, month, holiday, working day, weather parameters, all of them. So instead of creating several data frames and then concatenating them separately, I have just written a for loop where at the end I'll get an output as a concatenated version of all the one hot encoded versions of these categorical variables. So if I just run this, you can see, so if you see the initial shape of the data frame was 731 rows and 16 columns, that is now converted to 731 rows and 37 columns. And if you have a look at that, you can see you can have columns like season underscore 3 underscore 4, year underscore 0, year underscore 1, weekday underscore 3, 4, and so on. So it's actually converted all the categorical variables into a one hot encoded form. So this data set is now ready for training for a linear regression object. So I'll leverage the train test split function under model selection to create for us a test data set and the train data set. So let's import the regression function. I'll say from sklearn.linearModel import linear regression. There we go. And I'll say model is equal to linear regression. Yes. Now we'll pass the actual data. So I'll say model.fit. I'll say x and y. So we have now created and fitted a linear regression model. So by default, you can use models. So now you need to actually go and predict the values. So let's say we create y underscore pred is equal to model dot predict, and we'll pass the actual test data set. So that will be x underscore test. So now we have y underscore pred with the predicted values for the test data set, and you'll have y underscore test, which will have the actuals of the test data set. So let's go ahead and look at how we can calculate the different metrics that we just discussed in the previous slide for this regression use case. So let's say we want to calculate the R squared value, the mean squared error, and let's say mean absolute percentage error. Mean absolute percentage error. Now, out of these, R squared and mean squared error is widely used in most use cases. So you have a direct function for them. Mean absolute percentage error is used, but not so widely. So we'll actually have to create that manually. So under sklearn metrics, we say from sklearn dot metrics, we'll import the different metrics which we just discussed. So we'll say R2 score, then we have mean squared error. So these are the two different metrics that we can leverage from directly from Python. So all you need to do is you say R2, and say score, R2 underscore score. We pass the true and the prediction values. So in the test phase, we have y underscore test. These are the actual values, and y underscore pred. These are the predicted values. If you run this value, you have an R squared of around 0.81, which is around 81%. Now that's a really good score. You can see around 81% of your test of the variance of y is explained by the model. Now this score is on the test data set. Let's see what would have the score been on the actual data set. So we'll say R2 score for y. So we first need to calculate the predictions of the test data set. So we can directly use a score function from. So instead of using R2 score, you can say model dot score and we say x comma y. So this is analogous to predicting the output for x and then passing it into R2 score as y underscore y and y predictions. We just directly use that, and I can say 85%. So we see that around 85% accuracy for R squared score for the trained data set and 81% for the test data set. The difference is not huge, but then overall you can say this is relatively a good model. Now, similar to R2 score, that is R squared score, we can actually have the mean squared error also. So we have mean squared error, and we pass y underscore test and y underscore pred. There we go. We have a huge number, 651297. Now these numbers will only make sense once you compare this value with several other models for the same use case. Now what if you have another model built with a couple of variations of the variable and you get a lower score? Now that implies that that model has a lower error score overall. So the last thing you want to do is you want to calculate the mean absolute percentage error. Now there are a couple of trade-offs in this metric because it doesn't really amplify the larger errors, but still given that it gives you a percentage format of the error, it's relatively easy to comprehend the kind of impact your errors will have on the outcome variable. So how it will work is we'll take the sum of the difference between that is y underscore test minus y underscore pred. Now these differences are absolute differences, so we'll say absolute of these differences. Now that sum would be around 125705. Now this divided by the sum of the actual values, that will be y underscore test. So we have approximately 0.1247, which can be considered as 0.125. So that's a 13%, or approximately 13% error. Now you know the range of values you have in your y variable, and I'm giving you an approximate thing that on an average the model makes around 13% of error. So this number can be used to quantify what kind of errors you'll have on a test data set. Really easy and useful to understand, but then kind of there are a couple of trade-offs of directly using it. Now, in reality, you'll use a couple of them together and try to understand what is happening in the model. The moment we work on multiple versions of the same model, you'll actually see the differences between these scores, and then you'll be able to understand, okay, which model is performing better and which model has upper edge on a couple of parameters. So that's at a high level how we understand evaluation of regression models. Let's move on to understand how we can understand evaluating classification models.